So it's safe to clear. All right, I'll clear this out. Cool. So yeah, technically we already started this one. We took a look at it last time and we found that we weren't able to get quite to the end. We actually, we tried this, but it didn't work. And just to sort of summarize the thinking behind this one, it was that basically we had, we were representing this as a line. Actually, I have my Desmo sketch of this. So we were doing this basically. Notice the line is going in the other direction, but that doesn't really matter, you know, without loss in generality. It's pretty much the same as this thing. So this is totally fine like this. What we're going to do in order to check which ones are going to be shaded is we'll check, you know, take the 4 corners of each square, and we're using, where was it? Where was our formula? It was, yeah, well, yeah, it was this one. So it's the slope of this line over here times x minus y. And that's kind of like our standard form equation. That's going to tell us, well, basically, if that's 0, then it's intersecting the line. If this is positive, then it's, I think, below the line. If it's negative, it's above the line. Okay, so that means for something like this, since not all of these had the same sign, one of them was negative, the other 3 were positive. So that means we would shade this square. I'm not shading it very well, but anyway, you get the point, hopefully. Whereas this one, they were all negative in this case. So since they're all the same, we don't shade this square. So that probably seems pretty innocuous. It seems like, yeah, we can get that done, no problem. But then over here, the problem with that is, well, what if we were dealing with something on a larger scale? So like, for example, let's say, okay, how many do we want it to be? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And actually, you know what? I don't need to know how many there are going to be. This is just going to be like a pretty sloppy sketch, as it always is. And there we go. We'll draw the line. Chat's working for me, Augustos. I can see your message. Okay, so this will go across. Oh yeah, just like that. Okay, maybe not quite like that. Just like this. Yeah, okay, that's pretty not bad. Totally straight line, right? Okay, so then basically the idea here is that we want to shade some of these, right? But really not that many if you think about it. It's like this one, maybe this one, this one, this one, that one, that one, that one, that one, that one. You know, it's like, it's kind of okay. Like it's not that many is what I'm trying to say. So like if we're going through every single square here, we're wasting a lot of time, and too much time. In fact, look, we're exceeding the time limit, right? So we're spending too much time on that. Okay, so basically originally when I was going into this one, I was thinking, let's just forget this thing. It didn't work. We're going to move on. It was a nice demonstration, but it was doomed to failure. There was no chance it was ever going to work. And so I made a couple other plans. You know, I came up with a few other ways of doing this, and I was pretty happy with it. And then I realized, wait a minute, maybe this could work. Like just before we went live, I thought of an idea, because it occurred to me, like, the main thing that's wasting our time is the fact that we're going through every single one of these, every single one of these, every single one of these. Whereas, what if we didn't, you know? What if we just said, okay, so for each x value, we're only going to look at a few y values. For this one, just these. For this one, just these. For this next one, just these ones, you know? Like just these over here. Just, I don't know, maybe like these ones up here. So like if we restrict the range of our second loop in here, yeah, the y loop over here. If we restrict that, so instead of going from 0 to n each time, if it just went from like, whoops, wrong window. If it went from like, I don't know, from 2 to 4 or something like that, that'd be a lot more reasonable. So let's try that. Because I mean, like this thing is working for the first 9 here. It's just once it gets to 10, it times out because these numbers are too damn big. Makes sense. Okay, so basically, well, think about it this way, right? If we multiplied these two numbers, we'd have something huge. We'd have something way too big. Let's see how big that would be, actually. We've got a calculator here, right? 1, 2, 3, 4, 5 times 1, 2, 3, 4, 5. Let's run that. We'll see what number we get. That's too big. Guys, that's too big. It's not going to be able to go through this many iterations of the loop. Okay, so now let's say instead, let's say the 8ths one is the width. And let's say now that instead of going all the way from top to bottom, let's say it only covers like 3 or 4 squares. Let's say worst case scenario, it covers 4 squares. What number is it going to be in this case? Well, that doesn't seem too big. I mean, 350,000, it seems reasonable enough. So I think there's a decent chance this might actually work. The question is, how are we going to do this? So right now we have this f of x, y thing. This is basically our standard form equation, and it's telling us, yeah, so it's this, f at x, y. But what I actually want to do is go back to just the regular, like, yeah, this, right? Yeah, this, exactly, this. Okay, so this is just y equals n over m of x, or times x. Okay, so let's do that. We'll say function get y. Yeah, does that make sense? Maybe it should be like lower y and upper y. Yeah, let's do that. We'll do two of them. So function lower y, and it's going to take in an x value, and it's just going to return, what was it? It was n divided by m times x. Okay, so what I'm going to do is I'll do, for lower y, I'll do -1, and I'll take the floor of that. That should be enough, I think, right? To make sure we don't miss it, math.floor of this. And in fact, I just want to make sure that it's not going to go below 0. So I'll say, is it math.min? No, math.max. Math.mas of 0 and math.floor, etc., etc. Just so it doesn't dip below 0. That's basically it. And that's it. That's what it's going to return. And then we'll say upper y, which will also take in a value of x. And this time we're going to return math.min of, okay, which one are we treating as, yeah, okay, so n. It doesn't want to be, yeah, n minus 1 actually. It shouldn't be as big as n. Yeah. Okay, so n minus 1, there we go. And what else? Math.ceil in this case of n divided by m times x plus 1. Okay. I think that should maybe do it. Let's see. So this is going to be lower y of x, and this is going to be, let's make it equal to upper y of x. And I'm making it equal to that because this already is not going to go as high as n, so I don't think we need to worry about that. Is this going to work? Let's try running this thing and we'll see what happens. Hopefully I didn't like just totally break it or something. We'll find out, I guess. By the way, while we're waiting for this to load, I thought of a variation. Oh, yeah, I guess I broke it. Oh, well, hold on a second. This one's working now and this one isn't? Okay, so, hey, look, it's not timing out. That's good, right? It's not timing out. It's nice that it's not timing out. But there's some funny business going on with this one. I mean, this is not good. Oh, okay. Okay. Yes, I think I see the issue. I think. Yeah, okay. It's not going high or low enough, okay? So, like, in this case, we're talking about, like, okay, instead of like this, it would be rotated. So we're talking about, like, a tall long, okay? So, like, this kind of situation. We've got a tall long. And then we've got the line and it's trying to go like this. And so the issue is that if we're just checking like, oh yeah, just go from like from here to here. By the time it gets to the next point over here, it's not going low enough to actually shade the thing. So, okay, we need to keep that in mind. There are two ways we could keep that in mind. One way is that instead of just using the x value here, we could use the x plus 1 value. So, I don't know, maybe we could just do that. Like, if we just do plus 1 over here, is that going to work? Like, would that be enough to solve the issue? Yeah, I guess that is. The other thing I was going to say is we could also just switch m and n. Like, we could force it so that, what was the problem with this one? Which one was too big? Okay, so n was bigger than m. We could force it so that m is always bigger just by swapping them. So at the very start, we could just do something like if n is greater than m, then we'll just say n and m are gonna be swapped. And I love with the destructuring assignments how easy it is to swap two variables. We don't need any temp variables or anything like that. It's just nice and easy, it's simple, we don't have to worry about it. And I believe if I were to do this now, it should still work. Yeah, okay, so that's another way to do it. I don't know, does anyone have a favorite? Does anyone prefer one method over the other? Let me know if you do. But as for now, I'm going to try defeating the hidden tests. Let's see if it's going to run. Hopefully, but hey, if not, we've got other plans here. Oh, Oh, wow. I gotta say, folks, that feels pretty good. Like, I was ready to give up on this one. I was not planning on revisiting this kind of strange approach. Oh, well, look at that. Isn't that nice? We've completed the loop tunnel. Okay, good stuff. But keep in mind, we kind of want to find a way to do this without a loop if we can, because that's a little more slick, right? Not just that, but it's better for the time complexity, right? It'll execute better that way. So yeah, we should probably try to find some kind of constant time algorithm for this. I don't know if that's going to be possible. Maybe. We'll find out. Maybe we can at least do it in such a way that doesn't have 4 nested loops. I don't know. But keep in mind, okay, this is an important note. Normally when we see 4 nested loops, the temptation is to say, oh, okay, so it's big O of n to the power of 4. But in this case, that's not true. That's not the case. Because look at these loops. They're literally only going from 0 to 1, 0 to 1. That's constant. You know, these aren't going to take a longer time depending on the size of the input. These happen in a constant amount of time. Now, that constant time might be fairly big. Like if these did more, like if they went from 0 to 100, let's say, that would be a large constant time. But this, no, it's going to be a pretty small constant time. And we're just comparing those. Okay, so then before what we had was basically a big O of n squared, or n times m technically, right? Because we had this one covering all of the m values and this one was covering all of the n values. But we've turned it into more of just a big O of m in a sense, because this one really is only going to cover about 3 squares, you know, like depending on the case, maybe it'll be very extreme, but if it is a situation where this one is going to cover like a whole bunch of squares, then that must mean that the m value is very, very small, so we won't have to worry about it. So this is kind of nice. This is, I think, a good way of thinking about it. Like I said, we have some options here, so we don't need to swap these if we don't want to, but look at how efficient it is. Isn't that nice? I think that's nice. Anyway, cool. So this is working. It's good. Everyone's very happy. Everyone's really satisfied with this. But maybe it could be better. I don't know. I think it could probably be a bit better. Yeah, we might not be able to get that constant time algorithm. You know, that's the dream after all. But we'll find out what we do get. So, okay, I want to point something out. So I'm going to X that. We're going to confirm this. We're going to paste this back in. So it's just going to chill down here, not really affecting anything. I'll just do a run to make sure we're returning null at this point, and it looks like we're returning null at this point. Great. Okay, so what we want to do with this then is basically for this, we want to try to look at some patterns, right? Something I want to point out, and I sort of got started on this a second ago, I thought of a better variant or a more challenging variant on this problem. So I was thinking, like, they're just asking for how many shaded squares there are, right? If they wanted to make it a lot more tough, they could say, like, give these each an address, right? Say this is like 0, 0, this is 1, 0, this is 1, 1, this is 2, 1, right? So a more challenging version of the problem would be to say, give the addresses or the, what do you call those, coordinates of each one of the shaded cells in the order that the line goes through it. I think that would be pretty neat because it could be tricky, you know? You don't always know what order it's going to go through these in. So that would be a neat one, but I do want to point out they're not asking for that, so it doesn't really matter like where they are. We just need to know how many of these squares they're going to be. So something I want to point out is that in this case, it shouldn't actually be that difficult to predict because, okay, let me put it this way. We've got this line going through, right? So let's look at it going from left to right, let's say. Okay, going from left to right, it needs to go through a cell, at least, in every column. So there needs to be at least m shaded cells. There has to be at least 4 of them, right? Because it needs to go through at least 1 for every column. Now, we could also say it needs to work its way down from the top to the bottom. So if it starts at the top, you know, upper left corner, and it ends at the lower right corner, well, it's got to switch at some point, right? It has to switch from being the first y value to the second y value to the third y value, right? It needs to switch those. So basically, that means we're also going to have n minus 1. Now, if it's not clear why it's a minus 1, it's because it's going from 0 to 1 to 2. Okay, so the first cell is both. The first cell is both one of the n's and one of the m's. From there, we're basically saying, yeah, well, we're going to have one in each column. And also, the first one in that column is this n1. And then it needs to switch from being the first row to being the second row to the third row, and maybe more depending on the case. So the main thing, the main thing here is that we need to know how many of them there are. And my claim is that I think we could get a decent amount of mileage by just saying m plus n minus 1. Yeah, like that, minus 1. Let's see if that passes any of these. So it looks like it passed the first. Hey, it passed 6 of these. You know what? The order's bothering me. Let's switch this. Oh, that's much better. Okay, great. So it's passing 6 of them, but one of the ones that's not passing is this one right here, the 3, 3 one. So maybe let's try to figure out why that is. Well, notice here, it goes right through these intersection points. Okay, so since it goes right through the intersection points, that means we're basically getting an extra. You know, like normally as we're going through here, okay, I'm going to rephrase what I said before. We're basically going from left to right, and we're going to have at least 1 square in each column. Sometimes we'll have 2 squares in a column, and those are for the cases where it switches y values within that column. Okay, so in those cases, we'll have 2. Now, what I forgot to mention, and keep in mind, I'm assuming that we're going to do something like this, let's say, you know, like let's just say without loss in generality, we're talking about a case where the width is longer than the height, okay? So it's like, it's landscape mode. It's not going to be portrait mode. Although it's going to be kind of tough when we get into squares, but we'll cover that case in just a sec. So what I'm trying to say is basically this. Assuming it's a landscape rectangle, then basically we're going to have at least 1 square per column. Occasionally, we're going to have 2 squares per column. And that happens when it switches over from one y value to a lower y value within that same column. But what if it didn't do that within the column? What if it did that in between columns? Well, that would mean basically every time we have a situation like this, we're getting an extra. Okay. Normally, we wouldn't have all of these squares here if it wasn't going right through the bullseye in each of those cases. So instead of having 2 in a column, in that case, we'll have 3 in a column. So we get an extra. Okay. So the way we could say that is, and yeah, okay, we'll do this for now. What I wanted to say about this is basically this. So we'll say let shaded be assigned the value of this. Is that what we were calling it here? Yeah, shaded. Okay. So it's going to start at this value. And then we're going to do a loop. We'll say for let I be assigned the value of 0, I is less than m, I plus plus. And we're going to do a thing here. Actually, wait a sec. Just because it's always going to start here, and I don't want that to be confusing for our algorithm, I'm going to say start at 1, actually. Okay. And what we'll say here is basically, what are we going to say here? Well, basically what we want to say is at this point, if we have our n divided by m, so our slope, okay, multiplied by our x value, I'm calling it I here. Maybe I should call it x, just to be consistent with what we have downstairs and with our slope formula and all that. Okay, so there we go. So that's like our f of x, right? That's like our y value. And what we want to know is it going to be like a whole number? So the way we can check that is we'll do a mod 1. Don't often do a mod 1. It's kind of a strange thing to do, but basically what we're trying to check is if it has like a bunch of decimal stuff going on. So maybe it does, maybe it doesn't. And in fact, just to avoid the situation where we have to deal with, or potentially have to deal with like some floating point business, I'm just going to put all of the multiplication stuff up top. Yeah. Okay, cool. And so if that's the case, then basically we'll get an extra. So shaded is going to get plus plus. And at the end, we're going to return shaded. That's going to be the idea. So is that going to work? Let's find out. Hey, looks like it works. Okay, so that's kind of nice. That's pretty not bad, right? We like that, I think. Yeah, it's good. So I'm wondering if we actually need this one in this case, because, yeah, I'm not sure. Because, yeah, we already have n plus m minus 1. So I think by starting with this, it becomes like inconsequential whether the width is longer or whether the height is longer, because we're already counting all of our main cells here. We're just looking for the cases where we get a bullseye, in which case we need to iterate one more onto it. Okay, cool. So that's good, right? That was working, I think. Let's just make sure it's all good. We'll try submitting it, and there we go. Okay, good stuff. So that's all nice. That's all working great. We'll reset that. The thing is, it's not quite a constant time algorithm yet. It would be like, yeah, big O of M, right? So M could be as big as 100,000. So that means it could take some time to get this one done. Maybe there's a way we could get it done better. I mean, if you think about it, what we're really doing is this. We're saying return n plus m minus 1. I keep doing that. Minus 1 plus basically number of bullseyes. Yeah, something like that, right? That's pretty much it, because we're just adding 1 every time we get the bullseye, right? So how do we calculate that? Maybe there's like a quick shortcut that we could use to find how many of these direct hit situations we're going to have. And I mean, if we take a look at this, when does that happen? Well, basically it happens when I have some kind of common factor, right? Like in this case, they're both 3, so they're going to get a direct hit on every single one of them. But we can imagine a situation that's kind of in between the two, right? Let's use a visual so we don't have to imagine it, I guess. Let's make this 3 by 6. Hopefully I did that right. And then we'll have something going through, and there's a bullseye, there's a bullseye, and then, yeah, technically these are also, but you know, that doesn't really matter. So what were our dimensions here? It was 6 and 3. And how many of these did we have? We had 2 of them. Okay. And I guess how frequently do these come up? Well, basically it's when our multiples kind of line up in a sense, you know? So like 6 and 3, for example, we're basically going 2 to the right, 1 down, 2 to the right, 1 down. There's a 2 to 1 ratio between these two things, okay? So basically, if we can reduce these, then we're gonna have some of these direct hit collisions, okay? If they have common factors, then we're gonna have some of these direct hit collisions. Maybe we'll look at another example of that just to sort of prove the point a little more. I want to do a bigger one, so let's make it 12 by 8. Yeah, that should be good. So 1, 2, 3, 4, and then 1, 2, 3, 4. Yeah, that looks good, I think, right? And 1, 2, 3, 4. I'm just gonna put in some dots to sort of mark the way. Yeah, that's 4 as well. And there we go. Great. Cool. So there we go. And we basically have a situation like this where we want to go from here to here. Sorry, I keep switching the direction. Hopefully that's not too confusing or anything. We're kind of going to have, like, in a sense, a bigger version of what we had before in our first example, you know, because this was like a 3 by 4. And if you think about it, 12 by 8 would also reduce to 3 by 4. What I mean by that is 12 divided by 8 is equal to, 4 divided by 3, actually. Okay, cool. So we've got this situation happening. They're proportional to each other. So it's kind of like, you know, we have like a smaller version of the original problem. Wait, I must have done something wrong here. Is this not actually 8 or something? Wait, what did I do wrong? Oh boy. Oh, yeah, sorry. I totally messed it up, actually. Yeah, all of that. Whoops. It's, wait, hold on a sec. Shouldn't it be 4 by 3? No, it shouldn't. That would be 12 and 9. Oh, well, maybe we should just make it 12 and 9. Should we? No. We'll make it 12 and 8. They also have some kind of proportion, right? Whoops, okay. 12 divided by 8. What is that actually? what do they have in common? They have a 4 in common, right? So we could take that 4 and yeah, divide it out. So it'd be 3 over 2. That's better. Okay, so my mistake. Sorry, guys. That's one of them. And then that's one of them. And then that's one of them. Okay, so I must have been thinking of 12 by 9. My mistake. Glad we fixed that. All right, there we go. Yeah, so we've got a bunch of these little guys. And within each of them, we don't have any of those direct hit collisions. But overall, we've got 3 of them. Okay, and by the way, so this was 12 and 8. What is the greatest common denominator there? Greatest common factor? GCD of 12 and 8. Well, I think we said it was 4, right? Because that was the thing we divided the numerator and denominator by. So that was 4. In this case, we had, what, 6 and 3? So GCD of 6 and 3 is equal to 3. Yeah. Okay, so I guess I'll just zoom out a little bit. Yeah, we'll get all that on screen. Great. So here's what I want to say. I mean, basically, we see the GCD here, the greatest common denominator here, is 3. And we found that there were 2 collision points. Here, the greatest common denominator was 4, and we found that there were 3 collision points. So it feels like it's just 1 less than however many of these we have. And I guess that makes sense because we can sort of break these into these little sub-rectangles. This one doesn't really line up anymore, but that's fine. So we can break it into these like little sub-rectangles. And the number of sub-rectangles we have, well, basically each one of them is going to have a lower right corner, right? So we'll have a direct hit here. Lower right corner, direct hit. Lower right corner, direct hit, but that we're not counting that one. So that's why we're going to do -1. So basically 3 minus 1, it's 2. We have 2. 4 minus 1, it's 3. We have 3 of those. So that's basically what we're going to do. We're going to take the greatest common denominator. We're going to divide, not divide, we're going to subtract by 1, and that's going to be it. So I want to show you an algorithm that we can use for finding the greatest common denominator. I'm assuming this algorithm has a name, but I don't know it, so sorry. I would give credit if I knew who to credit for it. If anyone knows, let me know. But basically what we're going to do is this. At each step, we're going to do, let's say this is A and B, okay? So at each step, we're going to take B mod A, okay? This is going to be like our remainder, right? And in this case, well, B was 8, A was 12, so B mod A is going to be 8, you know, try 8 divided by 12. Well, it goes in 0 times with a remainder of 8. Okay, and basically we're going to say, is this 0? So equals 0? Question mark? No, it's not equal to 0. So what we're going to return is, here, I'll do a flow chart. So we'll say true and false, okay? Is it equal to 0? In this case, no, it's not equal to 0. So what are we going to return? We're going to return the GCD of B mod A, the remainder. So I'll put that in here, B mod A, and A. So in this case, if you think about it, all we're actually doing is we're flipping these because B mod A was 8, and then A was 12. So we're just rearranging them. It's kind of like the situation we were looking at before where we wanted to flip these guys right off the bat. So this algorithm is kind of cool because it does that by default. So it flips them if it has to. Okay, so then we're going to go through this again. This is no longer going to be the case because now we're going to do 12 divided by 8, which would go in 1 time with a remainder of 4. So now we're going to have a 4 over here for our B mod A. Well, it's still not equal to 0, so we're going to call this again. And in this case, B mod A is 4, and A is 8. Okay, cool. Oh, is this called the Euclidean algorithm? Okay, cool. Thanks, guys. Appreciate it. So basically, we continue this, and then, yeah, good old Euclid, eh? Lots of contributions to math. Anyway, okay, we'll continue this. So we've got GCD of 4 and 8. So then from there, we'll do B mod A, so 8 mod 4. Well, 8 mod 4 is 0. 4 goes into 8 2 times with a remainder of 0. Is it 0? Yeah, it is. So what do we want to return in that case? Well, actually, the 4, okay? What was the 4, though? Well, it was A, right? It was just our A value here. So that's basically the case. So let's get this in here. And then Where am I? There we are. There we are. Okay. Let's do this one step at a time. So we'll say function GCD, which will take two inputs, A and B. And it's going to say let remainder, or I'll make that a constant because this is going to be a recursive function. So it's going to be constant each time. So the remainder is going to be B mod A. Okay. And then we'll say if remainder, if it's greater than 0, then we're going to return GCD of remainder and A. Else, we're going to return A. Okay, so let's just see if this is working. So we had 12 and 8 before, right? And we found that it should give us 4. So we'll see if this is going to give us 4. And if it's not, we'll go back to the drawing board. If it is, then we can continue here. Let's just verify that that was, 12 and 8. That's the one I used in that order specifically. So this should sort of reflect what we were doing over there. It's 4. Okay, good stuff. Consistently, I think. Yeah, it's 4. Cool. Okay. Oh, just a sec. Okay, so Augustos asks, if we loop from 2 to math.min of n and m to find GCD, is it still considered to be O of n? Yeah, I think so. At the very least, it would be big O of math.min of n and m, right? And then it also, like, how would you do it from there? Basically, you try dividing each one of them to, well, technically, actually, hold on, Augustos, here's something I should probably mention. If that was the case, if you were going to do a loop, you should probably do it in the other order, right? Because as soon as you find a number that's going to divide into both n and m, then we're good. That's going to be the greatest one if we loop from the other direction, right? So we could cut it off early in that case. That would also mean if they're relatively prime, in other words, if they had a GCD of 1, we would have to loop all the way down to 1. But it's pretty much a guarantee that they will have 1, right? So yeah, we could do a loop like that, but it would be big O of n. Whereas this one, I'm not sure about the time complexity exactly, but since we're dividing each time, I would imagine it's going to be like a log situation, log of n, log of something. So yeah, basically, I think this is logarithmic time. Don't quote me on that. I might be wrong. You'd have to look it up. Euclidean algorithm time complexity. I suppose I could do that Google search right now, but not gonna. Anyway, the point is, just to make a visual what Augustos was asking, we could also do something like this, function GCD2, let's say, which will also take A and B. And in this case, we'll just say for let D be assigned the value of math.min of A and B, and D is greater than 0, D minus minus, and we would just say if A mod D is 0, and, where's my and? Oh, there it is, shift 7. B mod D is 0, then in that case, oh my god, return D. Okay, there we go. So let's try this, GCD of 12 and 8. Let's get that back. Oh, sorry, GCD2 of 12 and 8. So we want to see if that's going to run. And notice I put the return inside the loop here. The reason is because it'll always find one eventually. It'll always get to 1 and then say, okay, well, if D is 1, then you get this for free. Okay, we're just going to give it to you at that point, as long as these are like integer values, right, whole numbers. And I don't know why we'd be doing GCD with something that isn't whole numbers, but anyway. Okay, 4. Yeah, we're still getting 4. So that would work. I know it took a long time to actually like compute that, but I don't think that actually has to do with the computation time. I think that's just like server load or something like that. So yeah, I would say both of these are good. They both work. So whichever one you prefer. I think this one's going to be more efficient, and it's also recursive, which is kind of cool. There's also something neat we can do with this, because if you think about it, like remainder is actually a longer word than just B mod A. So we don't technically need to use remainder. We could just use a B mod A there and there. And also, if we think about it, like we don't need this else here, because if it doesn't return this, well, sorry, if it does trigger the if, then it's going to return. It's not going to go any further. So we could just put return at the bottom there. In fact, we could also just do something like this. Return b mod a, do a little ternary, right? And say GCD of b mod a and a, or a. Just do something like that. So now it's really getting efficient. It is taking quite a long time to load that up, think of the answer, but yeah, okay, still giving us 4. Let's see if this one's going to give us 4. And then while that's loading, let's maybe do it this way. We could say like const GCD is something that takes A and B to just this, right? Like I don't think it needs to be any more complicated than that. So that's kind of nice. I don't think we'd be able to write out this one quite as efficiently. Technically, we could turn it into a recursive function, right? Like we could say, we give it a third argument to represent D, and then just do like a D minus 1 on each additional call, something like that. But I think we're just going to stick with this one up here. It looks like the loading is a bit slow right now, so I don't want to spend too much time on this. Basically, well, what did we say the number of bullseyes was? I think it was like the GCD of M and N, or N and M, we'll just put them in order, minus 1, right? I think that was it. So because of that, I mean, really, we've got a minus 1 here. We've got a minus 1 over here. Yeah, still giving us 4. Okay, cool. That's good. So we could just do something like this, group it together and put a minus 2 on the end there. Let's try running that and we'll see what we get. And if that works, I think this is going to be our last one for this particular task. But we'll move on to something else after this, because there are lots of other like really quick ones after this, and they're going to be lots of fun. I mean, we're gonna breathe a sigh of relief after this problem. I think this one is a bit of a gatekeeper. It is kind of a tougher problem in some ways. It can be kind of hard to understand like this GCD stuff if we don't have like a background explanation sort of stuff. So, okay, great. It passed the sample test. Let's